There are a lot of situations that I cannot really design circuits using Karnaugh Maps. Let's look at this situation, for example. I have I'm building a circuit with a comparator. Okay, a comparator that creates the larger of the it creates a 1 when its A input is bigger than its B input. Well, if I look at this circuit, that's a circuit with 8 inputs and 1 output. Okay, problem with that is if I want to do 8 variable Karnaugh maps, that's a big map, and looking for implicants, prime implicants, essential prime implicants, looking for minimal realization and all that, that's gonna be long time before I can do anything. Okay, so obviously doing Karnaugh maps is not the right way. Let's look for other ways of doing it, and what I do now is I look at iterative circuits. Iterative circuits means that the circuits that they have something that keeps repeating. Okay, if you're comparing these two numbers 1011 1010, how do you do it? Well, you look at these two, you say, well, if these two are equal, okay, if these two are equal, I'm not making any decision. I'm going to pass the decision on to the next bit. If these two are equal, you say, well, again, I'm not going to make a decision. I'm going to pass the decision making to the next bits. If these two are equal, you say the same thing. But then when you get to this, when you find one that is bigger than the other, you say, well, the others couldn't make a decision, I'm making a decision. But then, if, for example, one of these, in one of these positions, you were able to make a decision, like in position number 0, 1, 2, 3, in position number 2, you were able to make a decision, you would say, well, I am able to make a decision, and therefore I announce that A is greater than B. Okay, well, let's do that logically. Okay, I'm gonna build a 4-bit comparator with a greater than output. First, I decide that First I decide that so far, not looking at any bits, A and B are equal, and therefore my equal input becomes a 1. Then I say this: if A is 1 and B is 0, okay, see, B is 0, that means a bubble here, a bar here, an inverter here. A is 1 and B is 0, that means there is a 1 here. Okay, if A is 1, B is 0, bit number 3, this position, has decided that A is greater than B, and let's ignore everybody else's decision. Because bit number 3, like for example, 9, 5, 6, 7, 3, 4, 9, 9. Well, as soon as you look at the 9 digit, you say, well, the upper number is bigger, so let's forget about whatever else others are saying. And therefore, if there is a 0 here, there is a 1 here, I decide that the greater is 1, and therefore I put an OR gate with a 1 there. On the other hand, if A and B are, look at the XNOR. XNOR, that means they're equal. Okay? I said that before, remember? When we talked about XORs, we said that if they are equal, the output is 1. Okay? If the output is 1, that means these two digits are not making any decision. Before that, I had decided that A and B are equal also. So if these bits are equal, and a 1 is coming from the outside, which is coming from the outside. Therefore, it means that so far my decision is 1. That means these two are equal. If this is equal, then I give the decision to bit number 2. If bit number 2 decides that A2 is greater than B2, okay, then bit number 2 is going to turn on my G output. On the other hand, if bit number 2 also says I'm not going to be able to make a decision, this one is going to be passed down to this gate and therefore leaving the decision up to bit number 1. If bit number 1 can decide, it will turn on my G output. If it cannot decide, it's going to pass on the decision to the lower bit, bit number 0. Okay? So, without having to do a 8-variable Karnaugh map, I was able to build this circuit. At the end, this is indicating an equal output, and this is indicating a greater output, and therefore I have an iterative circuit, a comparator that generates G, also an E input, an E output. A more iterative way of looking at it would be to say that each bit has an E input, a G input, an E output, a G output. This way, instead of having a big OR gate and this output, I have OR gates that keep adding to each other, meaning that this slice can be repeated as many times as you want for larger and larger comparators. A 16-bit comparator will have 16 of these cascaded together, and then the first E becomes 1, the first G becomes 0, and then you will get the final G and final E from the lower end of this circuit. Okay? This is the concept of iterative circuit, and another iterative circuit is an adder. Let's perform this addition. Okay? Adders as iterative circuits. 1 and 1 is 0. Okay? A carry of 1. 1 and 1 and 0 is a 0, a carry of 1. 1 and 0 and 1 is a 0, carry of 1. 1 and 1 and 1 is a 1 carry of 1. 1 and 0 is a 1 carry of 0. 1, 1 is a 0 carry of 1. 1 carry of 0, and so on. Okay? See, what I did was the following. I actually took 3 bits carrying A and B, and I repeated the same thing for all these slices. In each slice, I look at 3 values: the carry-in, the A input, the B input, created a sum output and a carry output to the next one. What it means is each one of these slices can be done by a truth table that has a carry input, an A input, a B input. Okay, let me put carry. And it has a sum and a carry output. Okay? And then I'm repeating this process for all these numbers. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 0, 0, 0 adds to sum of 0, carry of 0. Sum of 1, carry of 0. 0, 1, 1 becomes a 1, a 0. 1, 0, 0 becomes a 0, 1. 1, 0, 1 becomes 1, 0. 1, 1, 0 becomes 1, 0, 1, 1, 1 becomes 1, 1. Okay? So if I just build a little hardware that has an A input, a B input, a carry input, a carry output, and a sum output, okay, according to this truth table here, then I can repeat this hardware for as many times as I want to build whatever size adder I need. Okay, so let's build this. This is the truth table there. Okay. 0, 0, 0 gives me 0, 0, 0, 0, 1 gives me 0, 1, and so on. This is the Karnaugh map for the carry out part of that truth table. This is the Karnaugh map for the sum out of that truth table. The carry out is this, this, and this, and therefore AB, ACN, BCN. This one has 4 ones in a chess format or a checkerboard format, and the sum output is A XOR with B XOR with CI. Okay, actually the output is 1 when the number of ones on the inputs is odd, and therefore that's XOR of the 3 inputs. Implementing my carry out and my sum, this is what the hardware becomes. Okay, this is slightly different from the way I'm showing the expressions, but it's functionally is the same. Actually, I could do it this way. Okay, the circuit I'm showing here and here, they're basically functionally the same, but notice here that I'm taking this output from this middle exclusive OR and then using it for creating my carry output, which works the same way, but then this circuit I'm showing here has 1 fewer AND gate than the circuit over here, and therefore in most cases I'm going to be using this one over here, and I'm calling this a full adder. In order to build a let's say an 8-bit adder, you take 8 of these full adders and put them together into an 8-bit adder. An 8-bit adder, carry in, you put a 0 here, and then you have 8 inputs, A0 through A7, B0 through B7, and then 8 outputs, S0 through S7, and you also have a carry output. This becomes a an adder, AB, with a carry in, a carry out. Okay. Now if you need a 16-bit adder, take 2 of these, put them next to each other, that becomes a 16-bit adder. This is, well, what we have done is we started with, in a way, transistors, and we put gates together, but then starting here, we started talking about upper packages. Here, we build a comparator, okay? Here, we built an adder. Oops. Okay. Let's build something else, a multiplexer. This multiplexer has 8-bit inputs and 2 select inputs, and then it will select either one of the inputs and put it on the output. So it's a selection logic. Maybe here I have A, B, okay, this circuit, if S1, S0 is 0, 0, the output becomes the add of AB. If it's 0, 1, the output becomes the subtraction of A minus B. If it's 1, 0, the output becomes the multiplication of AB. If it's 1, 1, then the output just becomes the A input. So this way I'm showing you upper level constructs, upper level elements that can be put together to come up with a larger function. Here is a multiplexer. I can build a multiplexer using AND OR logic, and I've shown you how to take a 2-to-1 multiplexer, turn it into a 4-to-1 multiplexer. Okay, like that. Over here, I'm showing you this is I0, I1, I2, I3, S1, S0. Okay, this is using 2-to-1 multiplexer to come up with a 4-to-1 multiplexer. This is the same exact thing using AND gates and OR gates. If S1, S0 is 0, 0, I0 goes through 0, 0, I0, 0, 1, I1, 1, 0, I2, 1, 1, I3. Okay, the same exact thing as this circuit I'm showing on the upper right hand side, which we have already discussed. This is a 4-to-1 multiplexer. This is a 8-bit 4-to-1 multiplexer. All this circuit is 8 of these circuits on top of each other. Okay, we can build this using 8 of these putting on top of each other. This is a decoder. Okay, this is a decoder, and why we are talking about decoders, because starting here we started talking about upper level packages. We are not talking about gates anymore. We are talking about packages that inside them include several gates, and this is a comparator, this is an adder, this is a multiplexer, and now this is the decoder. Why do we use decoders? Well, decoders are used for selection of memory words, selection of devices, and so on. Here you have an ID number, I1, I0, and when enabled, if 0, 0, this becomes 1, 1, if I1, I0 is 0, 0. This is 1, or this is active. If 0, 1, active. If 1, 0, active. If 1, 1. Okay, and this is a 2 to 4 decoder. Why did I say active and then I first said 1, then I change it to active? Well, if I were to build this decoder and I wanted the outputs to be 1, this is how I would have to go about it. 4 AND gates, and then same thing, same logic here. Okay. If I were to build this using AND gates, in this case I1, I0 would 0, 0 would turn this one on to 1, and 0, 1 will make this one 1, 1, 0 will make this one 1, 1, 1 will make this one 1. Okay, if I were to build it using the AND gates, then I had to have AND gates, or I had to build AND gates out of NAND gates. Okay, because AND gates, I cannot use CMOS logic to build AND gates, and therefore I had to build NAND gates and inverters. It would mean that these would include 6 transistors. Okay, instead of using 6 transistors and using AND gates, I'm going to use NAND gates with one difference. Here, instead of saying If 0, 0 will turn this one to 1, I will say 0, 0 will make this output active. But then active is low. Inactive is 0. I'm sorry. Active is 0. Inactive would be a 1. And therefore, this is a decoder with active low outputs, and it also has an enable input. If the enable input is 0, that means inactive, then all outputs are inactive. In this case, inactive means 1, 1, 1, 1 on the 4 outputs. And if enable is active, that means it's a 1, then the outputs will be active according to the number on I1, I0. And active in this case means 0, another 1. Okay? Now we talk about activity levels. Actually, a NAND gate is the same as an OR gate with active low inputs. Okay? Actually, a NAND gate is the same as an AND gate with active low output. So I can either say an AND, or I can say an AND with active low output, or I can say an OR with active low inputs. Okay? When I'm drawing a circuit, I've already shown you this. When I'm drawing a circuit, it's a lot easier to represent it as such. See, when I see a circuit like this, I say, well, these two bubbles cancel out, these two bubbles cancel out, and therefore I have A and B, C and D ORed together. Therefore, W is A and B or C and D. On the other hand, if I wanted to extract that same expression from this circuit, I would have to do some Boolean, A NAND B, C NAND B, and then NAND them together and then do some manipulation. Eventually, I would come up with this expression. But this circuit, the one on the right hand side, is a lot easier to read than the circuit on the left. Okay, therefore I always draw my circuits using activity levels that match with each other and cancel out. Okay, I'm not talking about any different gates. Actually, when I want to build this, I will actually use NAND gates, but only to represent them. To make it more readable, I use OR gates with low activity levels, AND gates with low activity level and the output. The decoder you saw here is a decoder with active low outputs, and therefore this is how I'm going to represent it. It has an I1, I0 with active low outputs. It also has an enable, which is active high enable. If the enable had an inverter on it, then I would call this an active low enable input. In this situation, though, that doesn't exist. Okay? This is a multiplexer with active high. Well, let's not worry about the active high, with a tri-state output. If the output enable is 0, the output is tri-state, that means is Z. If the output enable is 1, then the output follows what it's supposed to be, which is, in this case, if S1, S0 is in this case, in the upper, if S0 is a 0, I0 will go through. If it's a 1, I1 will go through. Okay, so let's draw all the situations I have here. This is the multiplexer. Output enable. This is input 0, this is input 1, and this is my select input. Okay, and this is my output. If output enable is 0, this is gonna be Z, and that's it. Okay, doesn't matter what is on the other three inputs, it's gonna be Z. If output enable is 1, then then a 0 here would send this through. A 1 here would send this through, but the condition is that this has to be 1 for the inputs to pass through. Okay, what good does this do? Well, the good thing it does is I can cascade these together without having to have a multiplexer on the output. Say, if I have a 0 here, if I have a 0 here, there will be a 1 here, and therefore the upper multiplexer will take either this or this to the output. On the other hand, if I have a 1 here, the upper multiplexer, if I have a 1 here, this will be 0. The upper multiplexer will have a Z on the output. That means it's not driving its output. But then the lower multiplexer will take either this or this to the output. Okay? And therefore this is a 4-to-1 multiplexer using 2-to-1 multiplexers with the output enable or with tri-state outputs. Tri-state gates are always shown by a triangle on their output, as you are seeing in this situation here. Okay.